Welcome, ladies and gentlemen. I'm going to ask the junior partner to share which one of each pair of these integrals we can evaluate using previously studied techniques, and then which one we can't evaluate and why. So for the first pairing, x e to the x squared is my integrand versus x e to the x. One of these we can integrate using previously studied topics, and one we can't. So which one can we do? Grace and Riley?
The one on the left.
The one on the left, awesome. And why can't we do the one on the right?
Because the one on the right doesn't have the derivative of the exponent.
Absolutely. And so in the past we've seen products of functions, right? We've seen products of functions. In each case here we have a product of function as the integrand. But in the first case, right, one factor in the product is acting as the derivative of, right, the exponent or the chain rule component. So we can undo the chain rule, right? If we have the derivative of the exponent in this exponential function, then we know this would just come from e to the x squared. When differentiated, that would produce the exponential itself times the derivative of the exponent of the 2x. We didn't have the 2, so we'll take that into account by including a 1/2 in our antiderivative. And always a plus c. Raise your hand if you already have this. So you already have this? That's great. Awesome. Okay. Next pairing. Go ahead and share with the class which we can and which we can't and why. So which one can we evaluate using previously studied techniques? Kobe and Sophia?
We can do the right side.
We can do the right side. And why can't we do the left side?
Because the right side, the x isn't the derivative of the left side.
Absolutely. On the right side, the 1 over x, right? On the right side, the 1 over x is the derivative of this quantity ln of x. On the left-hand side, x, right, is not the derivative of ln x. And so again, two distinct parts, right? But one is the derivative of the other in the right side, just like one was the derivative of the other in the left pairing, in number 1. And then we've got two parts in the left-hand side where one is not the derivative of the other, it's acting as kind of that chain rule times the derivative of the inner function. So we'll put that on the back burner. We'll interpret this 1 over x as the derivative of ln x, right, in the base of a power. And so now I can go ahead and add 1 to the exponent, divide by the new exponent. And Tyler, we investigated our new notation, ln squared x, right, all over 2, plus c. And again, we could do a quick check. On any antiderivative, we could always check and see if we're correct by differentiating it and seeing if it produces the original integrand. So let's go ahead and try it. Ready? The derivative of ln squared x over 2, I'm going to pull that 1/2 out, and then do the derivative of a power function, exponent times the base raised to 1 less, times the derivative of the base, and the derivative of the base in this power function, ln of x, is 1 over x. Let's go ahead and grab my favorite pen, the cancel pen. 2 over 2 is 1. ln x to the first over x is my original integrand function. So we win. Hooray! Raise your hand if you get number 2 correct. You guys get this with number 2? That's cool. All right. And the final pairing, survey says, which one is integrable using previously studied topics? Brendan and Vivian. The one on the left. Who had the one on the left? Good to go. Yes. And then on the right, a product of 2 terms, but the 3t is not acting as the derivative of the inner function, right? And so I cannot, I'm not undoing a chain rule with the product on the right, but the product on the left I am undoing a chain rule. If I just had a, 6? If I had a 6t there, then I'd have the derivative of the angle, and I could go right to a trig rule. Is that right? 6t? But I didn't have a 6t, so I'll account for that in my antiderivative with a 1/6. What differentiates to sine must be opposite of cosine with the angle. Now if I do a quick check, negative 1/6, cosine differentiates to opposite of sine with the angle, then times the derivative of the angle is 6t, and cancel pen, 6. Negative times negative is a positive, and I get sine of 3t squared times t is equivalent to the original before we checked out the derivative of the angle of the 6. Awesome. So we'll go ahead and box that bad boy. And we'll be good to go. What questions do you guys have about your first 3? By the end of today's class period, we'll be able to handle, right, each of those other pairings, right? So we'll be able to figure out how to handle that. I'll pause the recording. We'll take care of our OTL checks. and then get after it. Thank you for your help in your assignment. Let's go ahead and take a look at how, right, we're going to undo those products where one factor in my product in the integrand function wasn't the derivative of the other part or a portion thereof. In other words, we didn't have the chain rule that we were undoing. All right, so let's go ahead and generate a new technique. It's called integration by parts, and it comes from my original product rule for differentiation, but we'll focus on a different product that's generated when we go backwards. So everybody, let's go ahead and use prime notation first, and then we're going to switch to differential at the end to get kind of our accepted notation that we see in most textbooks. So if I were to differentiate a product of two functions, each of them, right, a function of x, let's consider u times v. If I differentiated that product, I'd use the product rule for differentiation rules. Here we go. The derivative of a product of two functions is what? The derivative of the first times the second plus the first
times the derivative of
times the second.
I do that too.
Yes, absolutely. So what we're going to do now is we're going to switch over to our differential notation here in just a minute, but we're going to focus on this u times v prime. We're going to let that be the product in each of our pairings that we couldn't integrate. We're going to pretend that was the u times v prime. So what do I mean by that? I mean that this 3t sine t, right? One factor here is going to be the u. One of them is going to be the v prime. In this x ln x, one of those factors is going to be the u. One is going to be the v prime. In this x e to the x, right? One factor is going to be the u. One of them is going to be the v prime. Whichever one ends up being the v prime is going to take care of that dx part because it's a derivative. And we're going to switch to differential notation here in just a minute. But first, let's solve for that u times v prime, right? So that we can get a rule here to go backwards. So what I'll do is I'll go ahead and solve for this uv prime in blue. So I'm going to go ahead and do u v prime. And what would that be given by? Well, I would have to subtract over that u prime v in order to isolate the squiggle underline. So I'm switching order here, but I'm solving for that uv prime. So I would still have the uv prime minus u prime v. Everybody see that? Before we switch to differential notation, we're going to go ahead and now integrate because we wanted to find the integral of that uv prime product, right? We wanted to find the integral of that 3t sine t, the integral of that x ln x. So we're going to go ahead and integrate that both sides, all right, to generate our formula. So let's integrate uv prime, and again, our notation is a little crude here. Do you guys buy into the fact that we could integrate term by term just like we differentiate term by term? I'm going to include two integral symbols here then. All right. So I now have an expression. I'm going to find the integral of that product that I didn't know, u times v prime, and I'm going to switch now to differential notation. V prime we'll go ahead and say is dv in differential notation, the derivative of v. If we integrate this derivative, so again, the notation here is a little bit crude, but you guys buy into the fact that if we integrated the derivative, what would we get? Right, if we integrated the derivative of uv, what would we get? U times v. That's it. Minus, and then we'll just go ahead and switch the order here. U prime times v is the same as v times u prime. So in switching notation, I'll say v times du, just like we said v prime was dv. I'll say that u prime is du. This actually is my formula that will allow us to systematically generate the antiderivative of a product, u times dv. We just have to figure out what the u is, what the dv is, and we'll be able to apply this product systematically. We'll see exactly what this looks like. We'll do some practice together, and then you're going to have an opportunity to practice with your partner. So here we go. The integral of a product, u times dv, is given by u times v minus the integral of v du. And we're going to see exactly how this can be applied in each of our other pairings for the Bellwork. Let's go ahead and do this. So integration by parts provides us with a systematic method for undoing the product, right? Undoing a product in an integration. So the integral of u times dv is given by u times v minus the integral of v du. The idea is when we divide this up and rewrite, right, then we're left with a simpler integral in this part, right, that we know how to integrate, or at least is getting simpler. We might have to perform the process more than once in order to generate our final antiderivative. This provides us antiderivatives for the product rule, and we use when the integrand has two distinct parts, but one part's not the derivative of the other, and you saw that in Bellwork. In order to be successful with integration by parts, I'm going to share a strategy that my AP Calculus teacher shared with me back when I was in high school taking AP Calculus BC, and that strategy is just how to assign the priority. So how do we pick, right? How do we pick u so that du and the resulting substitution results in a simple integral? So priority for choosing u is an acronym that I affectionately call LIATE, like a Latin word, I don't know, that's made up, LIATE, where L is just an acronym. L stands for logarithmic functions. If there's a logarithmic function in your original product, always choose the logarithmic function to be u first. If there's no logarithmic functions, next in the order of priority would be inverse trig functions. So inverse trig functions are next to receive top billing. The A stands for algebraic functions like x squared or root x, and all those are algebraic functions. Next down on the list is trigonometric functions like sine or cosine. And last on the list are exponential functions. And if we think about the order of assigning priority here, as we get down to these lower ones, you see how, like trigonometric functions, their derivatives are kind of cyclical. Sine goes to cosine, goes to opposite of sine, goes to opposite of cosine, and around the horn forever and ever. Exponential functions are even worse. E to the x goes to e to the x goes to e to the x, and so they continue to cycle, versus these have more finite derivatives that end, right, and stop. All right, let's go ahead and take a look and see how this can be applied. So we've already dealt with one of these. We knew how to do the left side, so we're good to go on that. Check. What we didn't know how to do was the product, x e to the x, where one part of this product was not the derivative of the other. So what we're going to do is similar to u substitution in the sense that we need to take care of this dx. We're going to assign u and dv in my original integrand product. Then we'll generate the other pieces, du and v, and then just plug it into our integration by parts formula. The integral of u dv is given by u times v minus the integral of v du, and hope that that integral of v du now is easier. Let's see. Okay, let's go ahead and try one. So I'm going to go ahead and consider this product. There's two pieces here, and the dx has to be included. And one of them, that's always going to be included in the dv part, the dx. That way when I integrate back up to get the v, right, I'll be able to do so. So let's go ahead and choose u, and let's choose dv. That's for my original integrand. I look at my order for assigning priority, LIATE, and I see that logarithmic, inverse trig, algebraic, trigonometric, exponential. As I look at this, I know that exponential is last on the list. I don't want to choose exponential to be u unless I absolutely have to. But this algebraic part, this x, right, that's higher than the e for exponential, so I'm going to let u be x. Then the remaining piece, that e to the x dx, that's going to be dv. So e to the x dx is going to be the dv. Notice how my entire integrand is accounted for. I've accounted for the x, the e to the x, and the dx. They're all accounted for. There's my u dv. So this is really the integral of u dv. But I need the other pieces in my formula. So from u, I need to get down to du. And from dv, I need to go up the ladder to v, and then I'll have all my pieces, a u, a v, du, and a dv, and I can just plug in. Here we go. If u is given by x, then du is equal to dx. If dv is given by e to the x dx, then going up the ladder, that is integrating both sides to generate v, I would find the integral of e to the x with respect to x. Can I do that? Yeah, what's the integral of e to the x with respect to x? E to the x. So what we've done is we've broken up our original product. We're trying to make our original product integrand function, right? U dv. I've chosen u and dv to fill up my entire product. I've used my definition for u and dv to generate the other pieces of my formula, that is du and v, and now I'm just going to plug into my formula. The integral of u dv is given by uv minus the integral of v du. Kobe?
Why isn't du just 4?
Why isn't du just 1?
Yeah.
It is 1 du. Right? The derivative of u is 1 du. He's asking why isn't x?
Like x
Yeah,
equal to
yeah.
1. Why do we have dx, not just 1?
Oh.
Like constant.
We do, but we're working with differential notation. So this is 1 dx. You know, the derivative of x is 1 dx. The derivative of u is 1 du. But we need to have our differential notation so that when we plug in, we have a dx or a du, right, to go along with our integral symbol. Otherwise, we're not authorized to find an antiderivative function because we don't know what the independent variable is. So every time we write an integral, we have to have a du or a dx, right, in order to integrate. We can't just have the integral of e to the x. We have to have the integral of e to the x with respect to x, so I know what my independent variable is. So yes, this is 1 dx. Yes, this is 1 du. All right, let's go ahead and try that. So I know the integral of u dv is given by u times v minus the integral of v du. Let's see what this looks like when I make my substitution. So here we go. The integral of, what was u? X. What's dv? E to the x, e to the dx. Does that match my original? That's the answer we're trying to figure out. We're trying to find the antiderivative of x e to the x with respect to x. All right, well, it's given by u times v. So what's u? X. What's v? E to the x. Minus the integral of v du. What's v? E to the x. What's du? Dx. And now we see why we needed this to not just be 1. We need it to be 1 dx so that I have, with respect to the independent variable, when I have this integral symbol, so I know, right, what my independent variable and my antiderivative function will be. So we have to have this dx here. So did substitution into my integration by parts formula result in a simpler integral? Yes, because now I know how to integrate this, which means I'll know how to get an antiderivative for my original problem. So I know that my antiderivative will be x e to the x minus the integral of e to the x with respect to x is just e to the x. So then I get x e to the x minus e to the x. And then, of course, we still need a plus c. What? So the antiderivative of x e to the x is x e to the x minus e to the x plus c. Ever the skeptic, not sure. How can we check? Well, let's differentiate and see. So I'm going to differentiate this and let's see. What's the derivative of x times e to the x? Well, that's a product rule. The derivative of the first times the second plus the first times the derivative of the second minus the derivative of e to the x is plus the derivative of constant. Oh, where's that cancel pen? Positive e to the x minus e to the x is just 0. And guess what? It differentiates to my original x e to the x. How bomb is that?
Pretty bomb.
Pretty bomb. That's pretty bomb. All right. So by systematically choosing u and dv to fill up my original integrand as a product, I can use my integration by parts formula, right, to find an antiderivative function. Let's try another and see how it works. And as we get better at this, right, then we'll be able to tackle more complex integrand functions. So which of these, right, we already knew how to do the right side because this 1 over x was acting as the derivative of the base ln of x in a power function to the first. Let's go ahead and choose my u and v. So we already are done with this one. We know how to do that one. All right, so what do we do? Well, we'll go ahead and choose u and dv such that I fill out my original integrand product. All right, so I go to my Liate and I scan the problem. Are there any logarithmic functions? Yes, so I'll choose u to be ln x. That just takes care of this part of the integrand. I still need to account for the x dx. Well, I'll let dv be the other part, the x dx. Does this fill up my integrand and would result in the integral of u dv? Yes, it does. That's the first part of my formula. I need the integral of u dv. That's taken care of. Let's generate the other pieces of my formula. So if u is ln of x, then du is 1 over x dx. If I'm using the differential notation, when I differentiate u, that goes to du, the derivative of u, and the derivative of ln of x is 1 over x dx. When I integrate dv to generate v, right, I need an antiderivative for x with respect to x. Can I do that? Yeah, I just x squared over 2. Are you going to x squared over 2? Do I have all my pieces?
Yep.
Let's go ahead and plug into my formula. I know in general, the integral of u dv is given by u times v minus the integral of v du. And if we followed our priority in assignment, hopefully this integral of v du that finishes out my formula is a simpler integral than my original, right? So let's see if that's the case. The original substitution then would be integral of ln x times dv is x dx. Is that everybody? Yeah, that's everybody accounted for. Equals u times v, so that would be x squared over 2 times ln of x minus the integral of v du. V is x squared over 2. Du is 1 over x dx. Is this resulting in a simpler integral than my original? Yeah, it is. I can do a little algebraic simplification here and get x squared over 2 ln x minus, that becomes just x over 2. The integral of x over 2, is that what you guys are getting? With respect to x? Yes? Awesome. And what's that? Well, this is x squared over 2 ln of x, and this is just a power rule x to the second over 2, so I get times 1/2, so I get negative 1/4 x squared plus c. Is that what you guys are getting? Yeah? And just pull the 1/2 out front and then do x squared over 2. Is that what you guys are getting?
Yes.
All right, let's check it. All right, I'm always hesitant. Let's go ahead and check it then and see. So I'm going to go ahead and check to make sure that we've generated an antiderivative for x ln x. Okay, let's go ahead and see. Here we go. The derivative of a product of two functions is the derivative of the first. So 1/2 times 2x times the second ln of x plus the first x squared over 2 times the derivative of the second, 1 over x, minus the derivative of 1/4 x squared is 1/4 times 2x, plus the derivative of a constant is 0, so let's go ahead and see. Ready? 1/2 and 2, x ln x. X squared over x is just x. 1/4 times 2 is 1/2, and x over 2 minus x over 2 is just 0, so I'm left with my original x ln x. You guys see that? That's pretty sweet. Dang. Love it. Math works. That's pretty cool. Third one? Yes? All right. So we already know how to do the first one because the t is acting as part of the derivative of the angle, right? In accordance with the chain rule, we can undo the chain rule. On the right-hand side, we've got too much t, right? We've got too much t. We have a product of two distinct functions where one is not acting as the derivative of the other. So what do? Well, we'll go ahead and assign priority when we choose our u by using our Liate acronym. So let's go ahead and choose our u and our dv. I'm going to go ahead and go down Liate. It looks like I want to choose which to be u, the 3t or the sine t.
3t.
The 3t, that's algebraic. That's going to get top billing for assignment to you. I mean, we could obviously pull the 3 out in front so we didn't trip over it if we wanted to, or we could leave it right here. dv then was going to be the remaining piece, so that would be sine t dt. So dv is sine t dt. Have we filled up the integrated function entirely? Yes, we have both pieces. Now let's generate du. If u is 3t, then du is 3 dt. Everybody see that? We differentiated that. If dv is sine t dt, then v is up the ladder, so what would that be?
Opposite cosine.
Opposite cosine t. Alright, so we've got the integral of u dv is given by u times v minus the integral of v du. Let's go ahead and see what we get. So my original u dv is 3t sine t dt. Is that my original? Yep, and it's given by uv is going to be negative 3t cosine t. That's u times v minus the integral of v du. V is negative cosine of t, so minus the integral of negative cosine t 3 dt is going to be plus 3 cosine t dt. Did we get the signs right? So minus a negative plus a positive, the 3, the cosine t, and the dt. Everybody good? Did substitution result in a simpler integral? Yes, we have an antiderivative for 3 cosine t, so we'll be able to finish this out. So it looks like negative 3t cosine t. What differentiates to 3 cosine t? Positive or negative? Positive, so plus 3 sine t plus t. So negative 3t cosine t plus 3 sine t. And just like the previous, we could always differentiate this and check to make sure we generate the original. Do you guys want to differentiate this, or we're okay? Okay, so you're welcome to go and check that out later. We've already differentiated our previous results, and so you can do that anytime to check, obviously. All right, let's keep the party going then. So let's try some more. In my original integrand, this is a little bit different, right? We're not thinking we don't have two different functions of u. Well, we kind of do, right? The dy is going to be able to act as that dv, and then when I integrate, I can still get a v and a y, and I'll be able to complete my substitution. Top billing goes to Liate. The I is inverse trig. I is inverse trig. That's up close. And so let's go ahead and choose our u and our dv. So Liate, the I is for inverse trig. Inverse tangent of y is going to get the u assignment. So inverse tangent of y is going to be u, and then dv is just dy, and that takes care of my entire integrand. You guys see it? There's my integral of u dv. Great. So then what's du? Well, if u is inverse tangent of y, then du must be 1 over 1 plus y squared dy. So if u is inverse tangent of y, then du is 1 over 1 plus y squared dy. If dv is given by dy, then b must be what? Y. That's it. All right, let's go ahead and complete our substitution then. We know that the integral of u dv is given by the product u times v, so that's going to be y times inverse tangent of y, minus the integral of v du. What's v? Y. What's du? 1 over 1 plus plus y squared dy. Did my substitution, right, result in a simpler integral? Well, yeah, at least one, I don't know what you call simpler, but we certainly know an antiderivative for this, right? We've got a y that can act as part of the derivative of this quantity on bottom to the first power. So what overall rule is this right side going to be? Natural log, comma, baby, right? And we always include absolute value bars even though they're not needed here, because 1 plus y squared will always be positive, but we'll still do it for safety first. So y inverse tangent of y minus, I need a 2 to provide 2y dy, the derivative of my angle, yes?
Yes.
I need a 2, cancel out with the 1/2. So minus 1/2 ln of absolute value 1 plus y squared, close bars, plus c, knowing that 1 plus y squared will always be positive, but it's a good bad habit. No, a good bad habit to have. It's a good
The bad good habit.
bad good habit to have. Oh, thank you. That makes more sense. Yes. Love it. And of course we can check by differentiating. And I'm encouraging you to do so after class. What questions do you guys have so far? That's pretty cool. Because honestly, we didn't have an enduro for that before. Now we have a strategy. That's pretty cool. All right. X secant squared x dx. You guys want to try this one with your partner?
Yeah.
Yes. I'm going to go ahead and pause it, and we'll come back and check. All right, ladies and gentlemen. So top billing goes to algebraic over trigonometric. Raise your hand. Get the same assignments and the same generations for du and v. Good. Now let's plug it into our formula. The integral of u dv is given by u times v minus the integral of v du. And you might be thinking, is this an antiderivative that I now know? Well, yes, we may have forgotten, but we did generate, all right, an antiderivative rule for tangent last year. By thinking about tangent as a quotient, sine over cosine, we could see that this sine of x here is acting as part of the derivative of this quantity cosine of x on the bottom to the first power. So this is actual natural log. If I had a negative here, I could go natural log of absolute value of cosine of x, right? So if I had a negative here, this would be natural log of absolute value of cosine of x, and I didn't, so I have to provide that. And so an antiderivative for bless you, tangent of x is negative ln absolute value of cosine of x, which is equivalent to ln of absolute value of secant of x, which is what we wrote down. Now, notice that we also have a negative here, and so I could do plus ln of absolute value of cosine of x plus c, or I could do minus ln of absolute value of secant of x plus c. Either one is correct. And so which one did you guys do? So you did positive ln of, okay, so we'll go ahead and write our final answer then as x tangent of x plus natural log of absolute value of cosine of x, close bars, plus c. And raise your hand if you had this. So who was able to successfully generate this? Yes! That's great news, you guys. Good job. All right, let's keep the party going then. Who? Are there two parts here? There are. Again, we'll go ahead and consider that dx acting as the dv. Let's go ahead and do, this is a classic problem. So this is a classic one. We didn't have a strategy to undo ln of x, but you see this in almost every, right, in every text or class or calc 2. So it looks like I'm going to choose my u and my dv. Liate, top billing goes to logarithmic functions. So I'll let u be ln of x. dv is going to be the dx. Is my entire integrand function taken care of by u dv? It is. There's my ln x dx. So I can generate my other pieces, du and v. If u is ln of x, then du is 1 over x dx. If dv is dx, then v is x. Now we can go ahead and complete our original problem. The integral of u dv is given by u times v minus the integral of v du. Did our substitution result in an easier integral? Yeah, look at that. X over x is just 1. So the integral of 1 with respect to x is x. Guess what? Classic. Antiderivative for ln of x is x ln of x minus x. Plus c. Thank you, kind sir. Alright. This plus c is going to get lonesome over there. We're a little bit closer. Alright. This one we can check because it won't take time. The derivative of a product is the derivative of the first times the second plus the first times the derivative of the second minus the derivative of x is 1. And I get ln x plus 1 minus 1 is just ln of x. So this one checks out nicely. Yeah. Awesome. Okay. So thus far, we've developed a systematic procedure, right, for generating antiderivatives where we have a product in my original integrand, where one piece is not the derivative of the other in accordance with the chain rule. I've got too much or unrelated functions. Such is the case with this one. But for the first time, we're going to run into a minor obstacle. So let's go ahead and choose our u and our dv. Based on our current integrand, what would you select u to be? Go ahead and tell the class when I call on you. So what would you choose when I call on you? What would you choose the u to be based on this integrand? Right. Sydney?
Sine of x dx.
So, for you?
Oh, for you?
Liate.
Oh, gosh.
Liate.
Well, oh, x squared, algebra.
Yes, algebraic is one rung on my priority ladder above t for trigonometric. So yes, I'm going to choose x squared. And dv then would be my sine of x dx. All right, so let's generate our other pieces. Du and v respectively. So if u is 2 x squared, then du is 2x dx. If dv is sine of x dx, then v is always mess these signs up.
Oh,
It's negative.
Opposite cosine of x.
I didn't.
Yes, you guys good? All right, so let's go ahead and do our substitution. I know the integral of u dv is given by u times v, so negative x squared cosine of x, minus the integral of v du, and v was minus, so I'm going to make that plus. V du 2x cosine of x dx. Did I get everybody?
Yep.
Okay. So did substitution result in an integral that I know a rule for? No. Did it result in a simpler integral though? Arguably yes. My original was an x squared power function. This is down to a 2x to the first linear power function. What do you think we're going to have to do? Round 2. We're going to focus in on this integral and now do another integration by parts with now u dv. Right? So we're going to do it again. Round 2. Which means that right from here, we're picking new u and new dv. All right, so what are we doing for u? 2x, algebraic. What are we doing for dv? Good. Du then is 2 dx, and v then is sine of x straight up, no sign change. You guys good? All right, let's do it. So I'm going to keep this first part. Negative x squared cosine of x. But now I'm going to go ahead and focus in on our minus integral of u dv for this one, right? And that's going to become the new u times the new v is plus 2x sine of x minus the integral of our new v du. Our new v is sine of x, du is 2 dx, so 2 sine of x dx. Did our second substitution, right, result in a simpler integral? Yes. Is it one that we have a rule for? Yes. So I know I'm at the end of the road. Good job. Cosine differentiates the opposite of sine, so this is plus 2 cosine of x plus c. How do you do? You get everybody?
Yep.
That's pretty awesome. So we had to go 2 levels, and we had our second degree polynomial times our cyclical trigonometric. And are you beginning to see why t is down lower on the list? Our trigonometric functions are cyclical, but our algebraic will chunk down. Nice. That's so cool. All right. So what would we choose u to be and dv to be for number 8? Quietly tell your partner, and then I'll call on you. So what are we going to have for our assignments in this case? All right. So what are we picking for u and dv? Courtney?
U is inverse cosine of x.
And dv is dx. Raise your hand if you have the same assignment as Courtney. Yes, let's do it. So inverse trig, top billing after logarithmic, and du then is opposite of 1 over square root of 1 minus input squared. Yes?
Yeah.
Committed to memory. Flashcards. Hashtag AB. Oh, v then would be x. Is that right? Yes?
Yes.
Cool. Let's do it. So the integral of u dv is given by u times v minus the integral of v du. That would be plus x over square root of, oh, I'm missing a dx, 1 minus x squared. Remember, when you go down the ladder and differentiate to get du, we have to have our dx. Which gives us a dx there. Did our substitution result in a simpler integral? Well, arguably it doesn't look simpler, but do we have a rule for this? Yeah, this is going to be what overall rule? Natural log? No, what? Thank you, Sydney. Oh, that's fun. It's going to have to be a power rule where this is equating the bottom to the 1/2, provided I have the derivative of the base. Do I have the derivative of the base? Almost. If I had a -2 here, if I had a -2x, then I would have the derivative of the base, and I could just add 1 to the exponent, right? -1/2 plus 1 and divide by the new exponent. But I didn't, so I'll have to account for that with a -1/2, which gives us x inverse cosine of x minus 1/2. Add 1 to the exponent. Divide by the new exponent. Dividing by 1/2, the new exponent is the same as multiplying by 2, and then plus c. And we can make this look prettier. X inverse cosine of x minus root 1 minus x squared plus c. That's pretty sweet. So an antiderivative for inverse cosine of x is this. That's pretty cool. All right, guys, we're almost there. All right, so what happens when our u priority, right, gets murkier and murkier, right? Based on our Liate, which I attribute to my AP Calculus teacher in BC back in high school. Liate, who are we going to choose for you? NDV in this one. Go ahead and share with the class when I call on you. It's going to have to be this time. Grace?
U should be sine of x.
And dv?
Should be e to the x dx.
Awesome, thank you. And so look, we've gotten down, right, to the low part of the ladder where we've got trigonometric, right, the Liate and the e exponential, right? So trigonometric wins, so we get u to be sine of x. Okay, let's get the other pieces then. Then du would be sine of x goes to cosine of x dx. And going up the ladder, v will be given by e to the x. Yes? Cool. So I've got the integral of e to the x sine of x dx is given by u times v e to the x sine of x minus the integral of v du, and v was e to the x du is cosine of x dx. I completed my substitution. Did it result in a simpler integral? Not really. it didn't really. But similar. Well, let's do round two. That worked for us before. I'm going to change colors, and again, I'm going to go with u dv du and v. So what would we pick now? Well, still trigonometric beats out exponential for u assignment, so that would be cosine of x. So dv then would be e to the x dx. Cosine of x differentiates to opposite sine of x dx. Is that right?
Yeah.
And e to the x integrates to e to the x. Let's try. So we've got the integral of e to the x sine of x dx equals e to the x sine of x minus u v is e to the x cosine of x. Minus the integral, so minus the integral is plus a positive, the integral of v du, and that is e to the x negative sine of x. So I'm going to go back to minus here. Did I mess up my signs?
Nope.
Are we getting anywhere? My double, right, Decker assignment of u integration by parts has resulted in,
Round three.
isn't that exactly the same as the original? So we could go on ad nauseum and never get anywhere? Well, except that what am I looking for? I'm looking for the integral of e to the x sine of x dx. And I've generated an expression that has my integral of e to the x sine of x in it. What if I treat this as a variable like theta and solve this equation for e to the integral of e to the x sine of x? So let's add this to both sides like we would if we were solving for theta. I'm going to add this to both sides and get 2 times the integral of e to the x sine of x dx equals e to the x sine of x minus e to the x cosine of x. Could I solve for the integral of e to the x sine of x? This should not be sin dx, it should be sine of x. It's a sin to write sine without an input. So what do I do to finish this out? Simply divide by 2. That's it. How sweet is that? That's pretty cool. So my final answer is the integral of e to the x sine of x with respect to x is simply 1/2 e to the x sine of x minus 1/2 e to the x cosine of x plus c. That was awesome. And probably the most difficult that you'll run into, right? That you'll have to do. That was pretty cool. I like that strategy. All right, so let's close it up for the day and get you a chance
Oh, I can. Oh, I didn't.
to work together. Hey,
Woohoo!
Working right here, working for you 24/7, 365. When is it appropriate to use integration by parts? Don't say it out loud. Written response from everybody. Complete the formula the integral of UDV is given by. How does one assign priority for choosing U? And be ready to share. So when is it appropriate to use our integration by parts strategy? So when is it appropriate to use the integration by parts? Sophia?
When there are two parts, they aren't pairs.
Good. So two distinct parts, but one is not the derivative of the other, right? So one's not, right, part of the chain rule, not undoing the chain rule. Awesome. So whenever we have a product where the pieces, right, do not form the chain rule. And complete my formula integral of UdV with, right, with U's and V's would look like what, Brendan?
U times V minus the integral of E du.
Awesome. And let's complete our assignment for priority. Give me an L, Vivian. Logarithmic. Give me an I, Tyler.
Inverse trade.
Inverse trade. Give me an A, Riley.
Yeah, that's right.
True that, my brother. Give me a T, Sydney.
Trigonometric functions, such as sine or cosine.
Yes. Is it okay if I just put trigonometric? Give me an E, Marissa.
Exponential.
Yes.
Such as.
Oh, exponential. And everybody, what does that spell? Liate, huh? Very nice. All right, so you guys have a chance to work with one another. You don't want to have. Oh, so you might be thinking, Mr. Fritz, what's up?
Next slide.
You usually make us odds so that we can check our answers in the back of the book, to which I reply, yes. All right, looking out for you guys. Awesome. I'm going to go stop the recording. Strong work.
Where all the work was like right there.